Here we are in chapter 9. We are looking at one of the most common statistical tests, inferential tests specifically, in statistics, the independent samples t-test. This is one of the simplest experimental designs to have two different groups that you are comparing to determine if there's a significant difference between the groups. This test, although it is relatively simple, is not to be taken for granted. It's a very important test that we run, especially when we get to ANOVA. You'll see the importance of the independent samples t-test when we look at ANOVA's post hoc testing procedure. To say it's unsophisticated isn't quite accurate. It's one of the simplest tests that you can run. It's just two between groups. So we are going to take a look at it and see how important this test is, especially for foundational issues in statistics, because this is one of the most basic ways that we can look at experimental between groups methods. So let's go ahead and jump right into some of the characteristics of the independent samples t-test. Our two-tailed research question for an independent samples t-test is there a significant difference between two different samples? The one-tailed research question is there a significant increase or decrease between two different samples? That's not to say that we're looking for an increase or a decrease. What that means is that we are looking for either an increase if it's a one-tailed positive test or a decrease if it's a one-tailed negative test. The two-tailed hypotheses are that the null hypothesis is that the two groups are equal. M1 is equal to M2, so the mean of group 1 is equal to the mean of group 2. The alternate hypothesis is that the mean of group 1 is not equal to the mean of group 2. The one-tailed hypotheses are that either we have group 1 is less than or equal to group 2, or group 1 is greater than group 2. So if that's the case, then we have to pick one of those two for each of the tails, because remember, if it's a one-tailed hypothesis, you also have to pick if it's a positive or negative hypothesis. The null hypothesis is that the mean of group 1 is greater than or equal to the mean of group 2, or that the mean of group 1 is less than or equal to the mean of group 2. Now, I'll give you kind of a hint. We're really talking about the difference between two groups, but what we're trying to find out is the difference between those two groups different than 0? I'll say that again. Is the difference between those two groups equal to 0? We're going to take a look at what that looks like in just a second, but really we are looking to see in a roundabout way if one group is less than or greater than another group. Here's the big idea. You find the mean of each sample, which makes sense. If we have two different groups, we can find the mean of each of those two groups, no problem. We need to find the differences between the scores. So what is the difference between group number 1's mean and group number 2's mean? Okay, that tells us how far apart the two groups are. And then the hard part, the denominator, is to calculate the estimated population standard deviation of the differences between the means of the different scores. Huh? Yeah, we'll get there. It's okay. What we're trying to find out is what is the total amount of standard deviation in those two groups, so that we can find out what the average distance that those two groups are from 0. We'll get there, and it kind of makes sense in this next graphic. So let's go ahead and take a look at it. So here's the big idea. We have this big population curve. And what's interesting about that is that the population really doesn't exist. What this population curve is a situation where the difference between the two groups is 0. Now imagine if we have two groups, and let's say it's like a happiness scale. We have freshmen and seniors. We want to see if there is a significant difference in happiness between freshmen and seniors. And if the average for the seniors, or if use the right terms, if the mean happiness score for seniors is a 4, and the mean happiness score for the freshmen is also a 4, the difference between them is 0. So the null hypothesis is that the two groups are equal if we're using a two-tailed test, that the two groups are equal. So the situation that we are going to compare our result to is a situation where there is a mean of 0. And what we are comparing to that mean of 0 is the difference between our two groups. So imagine a situation, and let's just kind of use what we have here. Imagine a situation where we have two groups, and let's say it's seniors and freshmen. And seniors are group 1, freshmen are group 2. Let's say that on average, seniors score a 4. And let me back up. Let me flip this around so that it kind of makes sense mathematically. I can see that this is kind of get confusing. Let's back up a second. Let's say freshmen is group 1, seniors are group 2. Let's start there. If freshmen have a mean happiness scale of 6 and seniors have a mean happiness scale of 4, if you find the difference between those two groups, 6 minus 4, you would get a positive 2. So the actual difference between those would be a positive 2, and maybe it would fall like this on the comparison distribution. So really what we're looking at is, if we have a mean difference of 0, where does the mean difference between our groups fall? And if it's a positive 2, it'd be right around here, or whatever the scale is. It's just, maybe it's not proportionate, but this is just a demonstration. So the goal is to determine if the difference between two groups is significantly different than a mean of 0. Okay, you can see that we're not putting one group on one part of the curve, another on the other part of the curve, and seeing how far apart they are. We're looking to see how far apart the difference between the two groups are from 0. And if the difference between these two groups is significantly different than 0, meaning that the two groups are not equal, then it'll be far away from the mean. It'll be in the rejection zone. We could reject the null hypothesis. So again, we are testing if the differences between the means are significantly different from a situation where the differences are 0. So if we went back to our hypothesis testing, you could also write it as something like M1 minus M2 is less than 0. Okay, something like that. You could write it like that, as if the differences were different than 0, as opposed to comparing the two groups directly to say that one is less than the other. Either one is okay. We can roll with it. But remember, the big deal is that we are testing to see if the difference between the two groups, if the mean difference between the two groups is significantly different than 0. And the top of the equation is easy, just finding the difference. The bottom gets a little bit tricky. We look at the two top numbers and we want to find out the difference between the two groups and then divide it by the standard deviation of the distribution of the differences between the means. The S-diff is the standard deviation of the difference between the two groups. When we look at this, you need to remember to breathe. It's really not that hard. We want to look at the concepts, which will be listed on the right, but the formulas to get there, they're not really too tough, but they can be daunting looking at them all at once. So here we go. Okay. When we want to find out what the differences of the standard deviations are between the two groups, meaning we want to find out the standard deviation for each group and what the total amount of standard deviation is between the groups. I'll say that again. We want to find out what the standard deviation of the differences between the two groups are. So each group is going to have differences, and each group is going to have variance, and we want to find out what the standard deviation of the variances or the differences between the groups are. Let's walk through it. For group 1, we need to find out the variance for the sample. So in group 1, we can calculate the estimated population variance for group 1 by taking the sum of squares divided by degrees of freedom. That's the same as it was for the single sample t-test. And you do the same thing for group 2. So each group has a variance. Each group has a mean. Each group has a variance. So we find out what the variance for sample 1 is and the variance for sample 2. So far, so good. Now, if each group has its own variance, we can find out what the total amount of variance is between the two groups by doing what's called the weighted variance between the samples, or what we call the pooled variance. When we want to find out the total amount of variance between the groups, it's not just a matter of taking the variance from group 1, adding it to the variance of group 2, and dividing it by 2. That would be the mean variance, but only if the two groups were exactly the same size. And it's not always common that the two groups are exactly the same size. So we rely on what's called the weighted variance. And we do this. We assign each group a weight. And if the total weight is 100%, so 100% of the weight is between two groups, we want to assign a certain percentage to each group. We do that by taking the degrees of freedom in group 1 and dividing it by the degrees of freedom total. That tells us a certain percentage that group weighs. And then we do the same thing for number 2. We take the degrees of freedom in that group and divide it by the degrees of freedom total, and that gives us the mean amount of degrees of freedom in each group. Then what we do is we multiply that weight by their variance. So some amount of variance in group 1 will get weighed in proportion to the amount of people that are in that group. And then you add that to the second group and you have what's called the pooled variance. It's much easier when we look at the example, I think, even though this really isn't too bad so bad so far. So the next thing that we have to do now that we have our pooled variance all together is that we need to find the variance for each distribution of means. This is kind of quirky because normally we're able to very easily separate out step 2 using our rules and everything. With the independent samples t-test, we kind of have to go at it all at once. So when we create the distribution of means, because even though we have 2 different samples, we are still comparing it to a population, even though it's kind of this thing we're making up with a mean of 0. We still need to calculate the distribution of means in order to make the comparison distribution proportional to the average size of the groups, just like we did in chapter number 7. So it's pretty easy. All we need to do to calculate the estimated population variance of the distribution of means for group 1, he says easily, is take the pooled variance from above and divide it by group 1, the number in group 1, and the same thing for group number 2. This is just like in the single sample t-test when we would take the variance of the group and divide it by the number in the sample, and that would give us our variance for the distribution of means. Now, once we've calculated each group's variance of the distribution of means, all we need to do is add those together. And what that tells us is that's the sum of the variance of the differences between the 2 samples. Okay, the sum of the variances. So we add the 2 variances together, and that tells us what the sum of the variances of the sum of the variances of the differences between the 2 samples. Okay. Now, once we have the sum of the variances, or the sum of the variances between the 2 samples, which is the differences, we can take the square root of it, and we can get the estimated population standard deviation of the differences between the 2 means. So remember, we want to know how much variance is between these 2 groups. And once we do that, we create a distribution of means. And once we have that, we can calculate how far apart each standard deviation is on our comparison distribution. Now, once we've worked through these 1, 2, 3, 4, 5 steps, then we can plug this in. Our t-score, which will tell us how far apart the differences between our means are for our samples, will be the mean of group 1 minus the mean of group 2 divided by what we just calculated on this page. The estimated population standard deviation of the distribution of means of the differences between the 2 groups. Yeah, that's a mouthful, but it's right. You don't have to really understand each individual aspect of it, although I'd like you to. But here's what we did in this step. We found out the difference between the 2 groups. Okay, we found out how far apart the 2 groups are by subtracting them, and then we divided them by the average distance that each score is from the mean on the comparison distribution. Here's what it looks like. We have a comparison distribution that has a mean of 0. Remember, we're trying to find out if the difference between our 2 groups is significantly different than a situation where they're equal. If the 2 groups are equal, the difference between them is 0. So we want to find out where the difference between our 2 groups falls on this comparison distribution. Now, what we did in the last step is to find what the standard deviation of the comparison distribution is. You've seen this before. It just looks a little bit different because instead of just using estimated population standard deviation of the distribution of means, or S sub m, it's actually the estimated population standard deviation of the differences between the groups. Okay, because we have 2 groups, we want to find out what the estimated population standard deviation of the differences between the groups are. And when we do that, we get the amount of variance in each group, which we converted to standard deviation, and we added that to each standard deviation going to the right and subtracted it going to the left. And somewhere on here, and I know we're not dealing with numbers, but somewhere on here will be where our samples difference is and where our cutoff difference score will be. Because somewhere on here, we're going to calculate a t-score that tells us where the difference between the groups is significant. You know, maybe a t-score of 1.5 is significant. Maybe it takes a t-score of 2.2. We'll figure that out. But somewhere around here is going to tell us where the difference between the groups becomes significant. I want to run through an example using numbers that will help us to kind of understand how we calculate these things rather than just talking kind of nebulously about the concepts of it. So here's an example based on some random data, and whatever it is, I like to call everything a happiness scale. It's kind of optimistic, I guess. But let's say that we asked two groups of people about their happiness, and let's just say it's males and females. And let's say that the males responded like this. We had 5 males, and I said, how happy are you on a scale of 1 to 7? And they said, well, 2, 3, 6, 4, 7. So the 5 scores were 2, 3, 6, 4, 7. And for females, it was 4, 2, 6, 4, 5, 6. In order to determine the estimated population variance, I just added, I plotted my raw scores. I found my mean of 4.4. I subtracted each from the mean. I squared them. I added them together to get my sum of squares. And then I divided them by the degrees of freedom, or n-1, in order to get my estimated population variance. So we have, for the first group, for males, we have 4.4. For the mean number is 5. Degrees of freedom for group 1 is 4. And the standard deviation, the variance of the group, let me start over. The estimated population variance was 4.3. For females, they had a mean of 4.5 after I calculated that based on the data. The difference scores, the deviation scores were listed. The square deviation scores, we added them together to get the sum of squares. And then we divided that by the degrees of freedom, which in this case was 5 because there are 6 people in the sample. That gives us an estimated population variance of 2.3. So we found some information about the sample. We have a mean of 4.5, number of 6, degrees of freedom, which is n-1, equals 5, and an estimated population variance for group number 2 equal to 2.3. So as you can see right away, the variance in group 2 is different than the variance in group 1. The means are relatively close, but we'll see if that makes a difference. Now that we have this information, we need to go ahead and create the distribution of means by calculating that S sub difference variable. So we start by taking our pooled variance, and as you can see, that's the first step, is to find the pooled variance. We've already calculated the variance for each sample. Now let's find the pooled variance, or the total amount of variance in the sample. So the way that we do that is by taking the degrees of freedom in group 1 and dividing it by the degrees of freedom total, and multiplying it by the variance. That gives us a weighted variance. So 4 over 9, because the first group had 5 in it, the degrees of freedom is 5. The total degrees of freedom is the degrees of freedom in group 1 plus the degrees of freedom in group 2. The degrees of freedom in group 1 was 4. The degrees of freedom in group 2 was 5. 5 plus 4 is 9. So 4 over 9 times 4.3 plus 5 over 9 times 2.3. As you can see, when we have these two ratios, this 4 over 9 and this 5 over 9, if you add 4 over 9 and 5 over 9, you get 9 over 9, which gives us 1. That means that all of our all of our degrees of freedom are accounted for. So that means our weighted average will weigh out to 100%. So we we divide 4 by 9 and get 0.44 times 0.43 plus 5 divided by 9 equals 0.55 times 2.3. When we multiply those out, we get 1.89 plus 126, and then 1.89 plus 126 equals 3.15. This figure, 3.15, is the pooled variance between the two groups. The next step is to take our pooled variance and divide it by the number in each sample in order to get pardon me, I thought I saw a typo. In order to get the distribution of means for each group. So each group has a distribution of means because we need to take the really, really wide population curve and make it narrow. That way we have a fair comparison for the mean of our groups. So the estimated population variance of the distribution of means of group 1 is equal to the pooled variance for group 1 and divided by the number in group 1, which is 3.15 divided by 5, which equals 0.63. So our variance for group 1 went from, what was it? Up here. Went from 4.3 all the way down to 0.63. And the pooled variance for group 2 is calculated much the same way, and the variance in this case went all the way from 2.3 down to 0.52. So that was a significant reduction in variance because we are trying to create a distribution that is of the same size sample as our samples in the case. If we keep going, we see that the estimated population variance of the difference between the groups is equal to the amount of variance in group 1's distribution of means plus group 2's distribution of means. So when we add those two together, we find that the total amount of variance of the difference between the means is 1.15. And if we take the square root of that, we get the total amount of standard deviation between the differences between the two groups. Because remember, we're still comparing two groups and we're trying to figure out how much variance is between them, between their differences. And we get an overall standard deviation of the difference between the groups of 1.017. Which means that our new comparison distribution looks like this. Our comparison distribution has a mean of 0 because remember, we are trying to compare our results, the difference between our two groups, to a situation where there are no differences. So we start at 0, and the standard deviation, or the S-diff, is 1.07. So the first standard deviation is 1.07, and the second one is 2.14. Going to the left, it's negative 1.07 and negative 2.14. Here's what this means. If there is, let's say that there is a difference of 2.14 points between the two groups. Okay, so if one group's happiness scale was 2.14 more than the other, then it would be 2 standard deviations above the mean. Okay, that's kind of what that means. So if you are trying to wrap your head around what that means, all we're looking at is how far away is the difference between those two groups. Now, we see the comparison distribution, but we haven't talked about what the cutoff score is yet. How far away from the mean does the difference between our two scores need to be in order to be significant? Well, in step 3, we use the t-table again in much the same way we did for the single sample t-test. We will use a cutoff score that is for a two-tailed test at the 0.05 level with 9 total degrees of freedom. We use 9 total degrees of freedom. We find that for 9 degrees of freedom on a two-tailed test at the 0.05 level, we have a cutoff score of 2.62. Make sure I said that right, 2.262. What that means is that if the difference between our two groups has a t-score equal to 2.262 or excuse me, greater than, has to be greater than 2.262, then we have a significant result. If it is equal to 2.262 or lower, then we do not have a significant result. This is the same way that we calculate rejection and fail to reject situations for other tests. So again, if our result is between these two red lines that indicate the cutoff t-score, then we have a failure to reject situation, meaning that our null hypothesis is true, that the difference between the two means is not significantly different than 0. If the difference between our two scores has a t-score that is either to the right of the positive cutoff or to the left of the negative cutoff, then we have a significant result where we will reject the null hypothesis. In step 4, we have all the information that we need in order to put our t formula together. So the t formula again is t is equal to the mean of group 1 minus the mean of group 2 divided by the estimated population standard deviation of the differences between the scores. What that means is that we're going to find out how far away our scores are from each other to determine if they are different than 0, and then divide it by the average distance that the scores are from 0. So we take t is equal to 4.4 minus 4.5, so that's the mean of group 1 minus the mean of group 2, divided by 1.07, which is what we found back in step number 2. We do a little bit of math. T is equal to negative 0.1, so it's 1/10 of a t-score away from the mean, divided by 1.07, which is equal to negative 0.09. So the difference between our two groups, which was only negative 0.1, is 0.09 standard deviations away from the mean. Not far at all. Let's go into step 5 to see exactly how significant that is. So the null hypothesis is that mean of group 1 is equal to mean of group 2. In order for us to conduct this, to conclude this test, we plug in our information. Remember, for a two-tailed test, we are actually trying to find out if we can reject the statement that our score is greater than or equal to the lower rejection, or less than or equal to the higher rejection. So what that means is our score between those two rejection zones. And we plug that in by putting in the negative rejection zone, the positive rejection zone, so the negative cutoff and the positive cutoff for the two-tailed test, and then putting our value between it to see if that formula checks out. So there are two questions we have to ask ourselves. Is negative 2.62 less than or equal to negative 0.09? The answer is yes, so this half checks out. Is negative 0.09 less than or equal to positive 2.62? That answer is also yes. So both sides of these are correct, so that means we cannot reject the null hypothesis because it is apparently true. So we failed to reject the null hypothesis, which is the correct statement. So in this case, the difference between our two groups is not significantly different than 0. Let's go to another example and do it just linearly straight through so we can make some sense of it. So here's just a pretty simple example. What is your stance on caffeine? So the interesting part about this is that we could answer this a lot of different ways. Or we could theorize who would be the group that would have more of a stance on caffeine. But let's talk about morning people versus not morning people. You could theorize that morning people like caffeine better, so you could hypothesize a one-tailed test that way. Or you could say that not morning people like coffee better because it's the only thing that can get them through the morning. So let's just theorize for a moment that we have morning people liking coffee more than not morning people. Maybe that's why they're morning people, because they drink so much coffee. Maybe they're not morning people at all. Maybe they just like caffeine so much that they get up for it. I don't know. So on a scale of 1 to 7, where I couldn't care less about caffeine to I need it intravenously, we're going to ask just a very simple research question. So let's take a look at what that might look like. So is there a significant increase in caffeine consumption or the opinion on caffeine between morning people and not morning people? So population 1 will be morning people. Population 2 will be not morning people. We're going to theorize or hypothesize that morning people have a higher caffeine rating than not morning people. And then the null hypothesis, if that's not true, is that morning people will have a caffeine rating less than or equal to not morning people. What we know is that we are going to find the difference in the caffeine ratings between the two groups and compare that to a population. Remember, it's this kind of thing that we're building. It's not a real population, but we're looking at a population situation where the mean is 0. We want to know if the difference between our two groups is different than 0. So let's take a look at just some calculations. So in order to calculate the mean caffeine scale, I took each sample and I calculated the mean of each sample, 5.2 for morning people and 4.7 for not morning people. Sorry, I should have done a better job of labeling that, but population 1, population 2. I calculated their deviation scores, the squared deviation scores, the sum of squares, and then eventually I calculated the estimated population variance for group 1. I did the same for group 2, and I got an estimated population variance of group 2 of 5.9 and an estimated population variance of group number 1 of 1.36. We also have degrees of freedom for degrees of freedom in group 1 and 6 for the degrees of freedom in group 6. So again, we have a mean for the first group, for the morning people, a mean of 5.2, 5 people are in the sample, 4 degrees of freedom, estimated population variance of 1.36. For the not morning people, or population 2, we have a mean of 4.7, 7 are in the sample, 6 degrees of freedom, and estimated population variance of 5.9. Now that we have that information, we can go forward and find out what the standard deviation of the distributions of means is for these two groups using those series of calculations. I'm going to put them on one slide, so just bear with me that each step is across the page. So I've reiterated the information from the previous slide so we can refer back to it, but the pooled variance, so the total amount of variance between the two groups is the degrees of freedom in group 1 divided by the degrees of freedom total multiplied by group 1's variance, and then you do the same thing for group number 2. So I'm just going to do the equation across, so 4 over 10, so degrees of freedom in group 1 divided by the total degrees of freedom multiplied by that group's variance plus the weight of the second group, so 6 over 10, multiplied by that variance, which equals 0.14 times 1.7 plus 0.6 times 5.9 equals 0.68 plus 3.54 equals 4.22. So the pooled variance between the two groups is 4.22. The variance of the distribution of means for the first group is the pooled variance divided by the number in that group, or 4.22 divided by 5. Each is equals 0.84. And then the variance of the second group's distribution of means is equal to the pooled variance of that, the pooled variance of that group divided by the number in that group, which is 4.22 divided by 7, which equals 0.60. So the variance of the first distribution of means plus the variance of the second distribution of means will give us the difference, the standard deviation of the difference between the two groups. So the I said standard deviation, I meant variance. The variance of the difference between the two groups, which is equal to the variance that we found for groups number 1's distribution of means, plus the variance for what we found for the second group's distribution of means, which is equal to 0.84 plus 0.60, which is equal to 1.44. And whenever we want to get the standard deviation, we take the square root of the variance, which gives us 1.2. So the standard deviation of the difference between the distribution of means is 1.2. Okay, so we took the variance of each standard deviation, added it together, and that gives us the estimated population standard deviation of the differences between the distribution of means. Whew, that's a mouthful. Step number 2, I just brought forward my S diff, or my S of the differences, which is 1.2, and I plotted it on this new comparison distribution. So the comparison distribution that we are going to use to compare the differences between our two groups has a mean of 0, which is always the case. We want to see if our sample is significantly different than 0, and has a standard deviation, if you look at it in terms of t-scores of 1, which is how the t-scores always work, or the raw scores is 1.2 points. So 1.2 and 2.4, negative 1.2, negative 2.4. So if the difference between the means of our two groups is large, let's say greater than 2.4, for example, we're probably going to be somewhere in the neighborhood of significant, but we'll find out where that exactly is. This is just what our comparison distribution looks like. In step number 3, we're going to determine what the cutoff is. In step number 3, we want to determine what the cutoff score is. So in this particular case, we're going to use an alpha level of 0.05 or a cutoff p-value of less than 0.05, meaning that if our results are like occur less than 5% of the time, or are like the top 5% of scores on our comparison distribution, then we will consider our result to be significant, and we are using a one-tailed positive test because we are looking to see if morning people like caffeine more than not morning people. We have 10 total degrees of freedom because we have 5 people in the first group and we have 7 people in the second group. 5 minus 1 is 4, 7 minus 1 is 6, 6 plus 4 equals 10. If we look at our table, for a one-tailed test at the 0.05 significance level with 10 degrees of freedom, we have a cutoff t-score of 1.83. So 1.83 is approximately here on our curve. which means that we will have a significant finding, or we will reject the null hypothesis if our sample's t-score, if the difference between the two scores has a t-score greater than positive 1.813. Let's take a look and see what our sample's t-score is. When we plug our statistics into our formula, we get t is equal to the mean of group 1, which is the morning people, minus the mean of group 2, which is the not morning people, and divide it by the estimated population standard deviation of the differences between the groups. We get 5.2 minus 4.7 divided by 1.2. 0.5 divided by 1.2 is equal to 0.42. So the difference between our two scores has a t-score equal to 0.42, or just under half a standard deviation away from the mean. It doesn't look like we're going to reject the null hypothesis, but let's double check in step number 5. Step number 5, we bring forward our sample's t-score, and we compare that to our comparison distribution's cutoff t-score to see if our sample's t-score is less than or equal to our population cutoff score, and if it is, then we fail to reject the null hypothesis. Let's take a look. When we plug in our difference t-score, it is 0.42. Is 0.42 less than or equal to 1.83, which is our cutoff score? It is less than 1.83, which means that this statement checks out, which means that we fail to reject the null hypothesis. And this is in agreement with our graphical representation of where our mean falls on our comparison distribution. For the independent samples t-test, we have a results narrative that you can abide by in order to complete your data analysis, but this is what it would look like for our example. An independent samples t-test was conducted to determine if there was a significant difference in the caffeine scale from the morning people and not morning people. There was a non-significant difference between morning people, which had a mean of 5.2 and standard deviation of 1.3, and non-morning people had a mean of 4.7, standard deviation of 2.4. The t of 10 degrees of freedom is equal to 0.42 with a probability of 0.404. These results suggest that there is not a significant difference in caffeine scores in the morning people group compared with the not morning people group, which suggests a failure to reject the null hypothesis. I will tell you a couple of things. SPSS provided the standard deviation for the two samples. We could have easily calculated it using what we had available to us, but SPSS is fine to use for that. And also the p-value provided by SPSS. So the p-value was just something that I took right from their output. If you have any questions on any of that, certainly let me know. But SPSS is perfectly fine to use for getting some statistics from. Speaking of SPSS, when we use SPSS, we have a little bit of a challenge in how we organize our data. One is that we need a grouping variable for the independent variable. The independent variable is what we use to group by. For example, we had two groups in this example, morning people and not morning people. The condition that you are in, morning people and not morning people, is called an independent variable. You're familiar with that by now. And it has two levels, not morning people and morning people. So you have to create a variable that groups your cases, and the values will be in one column. So everybody who is in the survey, in this case, would be in one variable in one column, and all the scores will go in a separate column. We'll see what that looks like in class, or you can consult your book for that. Or you can look ahead to the data analysis videos that I've provided. Either is fine. The grouping variable allows us to look at the differences between the two groups within the grouping variable. Okay, so the independent variable will have two levels in this case, and I usually assign a 1 or a 2. 1 for female, 2 for male, or whatever it is. You just assign a 1 or a 2. That way you know which group each belongs to. And you need to give, in SPSS, you need to give those groups values. So group 1 will equal female, group 2 will equal male. You have to explicitly tell SPSS what the name of the variable's level is. So when we assign a value in SPSS, we need to kind of do it a little bit inside out. even though the number 1 and number 2 make sense, we need to tell SPSS what 1 means and what 2 means. And in some cases, you can use words instead of numbers for the groupings. I recommend not doing that because it gets a little bit confusing. And when you're looking at your data, and if you have to do any kind of manipulations with modifying a variable, you have to look at the names and you have to type in the full names, and it can be a pain in the butt. So we tend to avoid that by using numbers. So when you're doing that, we will go through an SPSS and we'll give it a shot. You can try it in SPSS before we have lecture if you'd like to. There's nothing wrong with that. Or you can wait until we're in lecture and we can do it together. So that is chapter number 8. Nope, chapter number 9, pardon me. Chapter number 9, it used to be number 8 in the previous books, and I'm having a hard time keeping it straight, although I think I've done pretty good so far. But that is chapter 9, where we are looking at comparing 2 samples from 2 different sets of people, and we are trying to determine if there are significant differences. And again, this is kind of an extension of the dependent samples t-test. We didn't cover it really in any detail, but it is worth knowing that it is an extension of a dependent samples t-test, except for that we're using 2 different groups. If you have any questions, please feel free to let me know. Otherwise, I look forward to seeing what you can do with your data analyses.